what we're going to do is we're going to look at redox reactions, or start looking at the terminology around it and some of the concepts. And a redox reaction is just a reaction which involves the transfer of electrons from one reactant to another. And in a process, this causes a rearrangement of the atoms often, and the formation of new compounds. Now, when we look at redox reactions, one compound will lose electrons, and so we say it's been oxidized or undergone oxidation, and one of the entities will gain electrons, and we say that's reduction. Okay? In our electron transfer theory, my total number of electrons that are lost by one entity must be gained somewhere else. I cannot have electrons lost or gained to the universe. Now, to be able to understand who loses electrons and who gains them, I have to have a firm accounting system for identifying who electrons belong to. And so I have to be able to assign electrons to things and give them what we call an oxidation state. What this is it's just an arbitrary value or an arbitrary way of assigning electrons. Now, when we're looking at ions, the assigning of these electrons or who they belong to is relatively easy. But when I have electrons that are involved in a covalent bond, whom those electrons belong to is very dependent on the electron negativity of the atoms involved in that bond. And so as a result, we have to have a way of assigning them and saying how many electrons an atom has, or an atom has lost or gained, or appear to have lost or gained when they're part of a compound or a polyatomic ion. And so we have our oxidation numbers that allow us to talk about how many electrons an atom appears to have lost or gained. Okay? And what we do is we assign electrons in covalent bonds to the more electronegative element. So if we take a look at water. Water is a relatively simple molecule for us to look at because we're very familiar with both its structure and distribution of electrons. And I've chosen not to include my lone pair electrons, but rather we'll just look at the two electrons in the bonding groups. So here I have an electron from oxygen and one from hydrogen to form this bond. And here I have one from oxygen and one here from hydrogen to form the second bond. So these electrons are shared and they belong both to oxygen and hydrogen. However, if I want to assign oxidation numbers, I have to give them to the more electronegative element. And since oxygen is more electronegative than hydrogen, I'm going to say that these electrons that are part of these covalent bonds all belong to oxygen. As a result, this makes it look as if this hydrogen atom has lost an electron and given it up. And so therefore, I would say that it has an oxidation number of +1. It has not lost the electron. But because we're assigning the electron to the oxygen, it has lost the assignment of an electron. And so it gets an oxidation number +1. Same thing happens for the hydrogen over here. The oxygen, on the other hand, because it appears to have gained an electron from one hydrogen, an electron from another hydrogen, appears to have gained 2. And so therefore, we would give it an apparent charge of -2, or state that it has an oxidation number of -2. Now, doing the Lewis structure and then assigning electrons to the more electronegative atom in a bond and doing a bunch of counting can be confusing. And so we need an easy way to assign electrons to atoms that are part of molecules or ions. And so as a result, we have a series of steps or rules for determining the oxidation number of entities. So the first thing is the oxidation number of any atom in their elemental state is 0. Doesn't matter if they're monatomic metals, for example, Fe solid would have an oxidation number of 0, or a polyatomic atom such as P4. They would have an oxidation number of 0 as well. Well, it makes sense for our polyatomic elements because they all have the same electronegativity, so we would have no apparent transfer of electrons. Okay, the oxidation number of an atom that is a monoatomic ion is equal to the charge. This makes sense too, right? So an F3 ion, or an iron 3 ion, would have an oxidation number of +3, because not only does it appear to have lost 3 electrons, but it's actually lost 3 electrons. The sum of the oxidation numbers in a neutral compound is 0. Well, this made sense with our previous example where my oxygen had a -2 and each of my hydrogens had a +1. So, and the sum of their oxidation numbers was 0. Likewise, the sum of the oxidation numbers for a polyatomic ion is equal to the charge of that polyatomic ion. Okay. Hydrogen has an oxidation number of +1 always, except if it's part of a metal hydride. So for example, LiH, lithium hydride. In that case, the lithium would have a oxidation number -1. In all other cases, because of its position on the periodic table and its relatively low electronegativity compared to other elements that can form covalent bonds, it'll have an oxidation number of +1. Oxygen, because of its position, usually has an oxidation number of -2. Now, there are 3 exceptions as to when oxygen will have an oxidation number of -2. The first is when it's in a peroxide. Well, this makes sense because in a peroxide, 2 oxygen atoms are bonded to each other, and then they each make 1 bond. So they're only each individual oxygen atom is only gaining 1 electron. If they're part of superoxides, in which case it's -1/2, or if they're part, they're in a molecule with fluorine, because fluorine is the only element that's more electronegative than oxygen, and so therefore the electrons that would be involved in the bond with fluorine would appear to belong to fluorine. Okay, and then we can also look at other things too to help us to determine oxidation number. Most importantly, all group 1 elements have an oxidation number of +1. All group 2 elements have an oxidation number of +2. Group 3 elements have an oxidation number of +3. And then when things are part of binary compounds, we can also use that knowledge. So let's take a look at a couple of examples to assign our oxidation numbers. So, potassium nitrate. We know in here we have potassium ion, we have a nitrate ion, and we have an oxygen ion. And we have to take into account the oxidation number of each of them. Now, because this is a neutral compound, we know that the sum of the oxidation numbers has to be 0. So we have oxidation number for 1 potassium, the oxidation number for 1 nitrogen, and the oxidation number for 3 oxygens. Well, we know because potassium is in group 1, it has an oxidation number +1. Oxygen is always -2. But what's nitrogen's oxidation number? What would it have to be for the sum of these oxidation numbers to be 0? So we can do a bit of quick mental math, or we can make ourselves a little equation. So +1 of potassium, x of nitrogen, we don't know what it is, 3 times -2 for oxygen, because each oxygen would have an oxidation number of -2. So we get that, and we find that the oxidation number of nitrogen in this case is +5. How about in this compound? In this case, because this is a polyatomic ion, the sum of the oxidation numbers is equal to the charge. So therefore, the sum of our oxidation numbers will be -2. We know that hydrogen is always +1. Oxygen is usually -2. And we're going to go with that. So now we have to figure out phosphorus. And we can do this in our head, or we can do the formula. If we did it in our head, we'd say 4 times -2 is -8, plus 1 would leave us at -7. So what do I have to add to -7 to get to -2? Right? 1 from the hydrogen, 4 times -2 for all 4 of my oxygens, and I get +5 for my phosphorus. Okay, one last example. Here we have a more complicated compound. But again, because there's no charge on this entity, some of our oxidation numbers are 0. Sodium being in group 1 is always +1. Hydrogen is always plus 1. Oxygen is always minus 2. We don't know what our chromium is yet, but we can do our equation. Plus 1 from my sodium, plus 1 from my hydrogen, plus 2x, because I have 2 chromiums of which I don't know their oxidation number, plus 7 times the oxidation number of each of the oxygens will be equal to 0. So I can add it all up, and I get 2x minus 12 is 0, so I get x is equal to 6. So chromium's oxidation number in this case is plus 6.